Sheila Langa from Hokkaido University. Or yours, Sheila.
Thank you very much. I'm Sheila Langa from the Space Transportation Systems Lab in Hokkaido University under the supervision of Professor Yusuke Takahashi, and this will be my presentation. We can go to the next slide, please. This is the main outline of my presentation, and in the next slide, I will be introducing the background and objective. So aeroelasticity is the main focus of my research, and it is a multidisciplinary subject that can be briefly explained by the colossal elastic triangle, as it can be seen in this diagram. And it can mainly be subdivided into two main groups, static aeroelasticity and dynamic aeroelasticity. In the case of static aeroelasticity, we have the interaction of elastic and aerodynamic forces, whereas in dynamic aeroelasticity, we have the addition of inertial forces. Inherently, as we can see next, dynamic aeroelasticity is a fluid structure interaction problem. Can you click, please? Which means that it is the junction of computational fluid dynamics with computational structural dynamics into what we call a fluid structure interaction problem. One of the most challenging transonic aeroelastic phenomena is called flutter, as we can see on the next page. Flutter is a self-excited or self-induced vibration that can lead to catastrophic failure. When it's observed in the transonic region, which is a very complex domain because of the occurrence of both subsonic and supersonic regions, this can lead to a lot of non-linearities in the flow, non-uniformities, as well as because of the occurrence of transonic dip. When transonic flutter has a limiting amplitude, it has what we call a limit cycle oscillation phenomena. And in order to solve this, we use FSI. Next, please. And that leads to my research motivation. As I was explaining previously, LCO is when flutter has a limiting amplitude, but it's a very complex phenomena because the primary sources of the nonlinearities that cause it are still a current topic of debate. They could be either on the solid case or the fluid case or both. Additionally, most commercial aircraft fly in the transonic region, and research in the area is pivotal, as well as recent configurations call for high flexibility and high maneuvers, and they may be sensible for nonlinearities that will cause aeroelastic phenomena such as limit cycle oscillation. So there is a need to research in the area. The main objective, therefore, is to contribute to research of transonic flutter and LCO phenomena, as we can see in the next point, by causing the causes and mitigation measures while discussing the merits or limitations of the proposed FSI model through validation of experiments and other numerical studies. And now we proceed to the modeling and setup. Next. For this study, we present an open source multi-physics coupling library called Precise. Precise is capable of providing data communication, data mapping, time interpolation, and coupling schemes. It works in a partitioned approach by means of adapters, and they provide the interchange data between the fluid and solid counterparts. For the CFD side, we are using SU2, and for the solid side, we use Calculix. Basically, the coupling method is as follows. Next, please. The aeroelastic problem is divided into a fluid and solid domain. Each are solved separately and joined at the precise interface. The fluid sends forces data and the solid sends displacement data. The solutions are met at the precise interface and they yield to one aeroelastic solution. In the next slide, we can see a brief description of the numerical parameters. Here we see that Calculix uses the principle of virtual work. SU2 uses compressible Navier-Stokes, and for Precise, we use nearest neighbor mapping. We have here two different versions because as the course of the research, there was an update in the system, so we updated to the newest versions. at the moment. Additionally, it's important to refer that all of the solvers use the same time step, which is 5e to the minus 4. In the next presentation, in the next slide, we see that the analysis model for this presentation is the crop delta wing model, which was experimented by Scherer and Hand, and has also been numerically validated, such in the cases of Attar et al. And Peng et al. The main difference between the numerically studied simulations here and my simulation is that whereas they used structured and unstructured meshes along with Euler and Navier-Stokes in their simulation, the current model uses a compressible, fully unstructured, open source-based partition coupling approach. As for the solid mesh study, we can see in the next slide, two meshing strategies were used, the coarse mesh model with 122,000 nodes and the refined mesh with 270,000 nodes. Additionally, for the fluid mesh, we can see a similar approach into the mesh strategies, where the coarse mesh has about 600,000 cells and the refined mesh has about 5 million cells. Both of these meshes have the same domain size, which is a 4x2x2 rectangular box, with the main difference that the refined mesh has the addition of prism layers on the wing interface. In terms of computational conditions, two viscosity models in SU2 were used. The coarse mesh model used the Sutherland viscosity model, whereas the refined mesh model used the constant viscosity model. This was done in order to match the experimental conditions. Now I will present the results. Can you go to the next slide, please? So prior to the FSI simulation, an EG frequency study was performed to validate the structural model. We can observe from the results that although mode 2 and 3 slightly differ from the experiment, mode 1 is consistent with 26.7 Hertz. And thus, we can also conclude that both the coarse and refined mesh, regardless of the refinement technique, they yield similar results. Additionally, in terms of the flow motions, we can see that all of the modes in the next slide, all of the modes have captured the similar behaviors as in the experiment, with first banding for the mode 1, first torsion for mode 2, and second banding for mode 3. Thus, we could conclude that the structural validity was in good agreement with the experiment. Next, a fast Fourier transform was performed to get the LCO frequency and the displacement. But before that, we analyzed the flow distribution. Here we can see that there is some shocks in the refined mesh case, and we also see that there is a great increase in the displacement for the refined mesh case. In comparing the surface mesh, as we can see next, we observe a vortex breakdown phenomena that is not seen in the coarse mesh case. This could be due to the difference in the flow conditions or the refinement technique, or it could be because of the occurrence of shocks in the refined mesh case and the capture of low pressure regions. Additionally, we can see that the main motion of the wing is the first bending mode. Next, we can see the LCO displacements and amplitudes. We can see that as we increase dynamic pressure, the LCO amplitude also increased, and the refined mesh model has a greater amplitude in comparison to the coarse mesh model. Additionally, we see that in terms of frequency, the refined mesh model has lower frequencies. In a general comparison, as we can see in the next slide, the refined mesh model has amplitudes that are similar to Attar's model. However, as we can see next, the region in the frequency between 3.15 to 3.45 psi, there is a constant or stagnant frequency range that was unusual and completely independent from the mesh refinement technique. This phenomena needs further investigation, and that is why we proceed with the dynamic mode decomposition. So for the dynamic mode decomposition, we focused mostly for the coarse mesh using a maximum number of 1000 safe time steps to capture the main dominant modes that affect the frequency and displacement of our model. We can go to the next slide, where we see the main dominant frequency modes in different dynamic pressures. We see here that the dominant modes, which are the first in each of the tables, are very in close proximity to the FSI frequencies. As we can see, mode 9 and 10 for 2.98 psi has about 50.75, which is similar to 50.8 from the FSI mode, similar to the 3.15 case. However, in 3.33 psi case, we notice that the frequency is different from the FSI frequency. So that means that DMD did not capture the stagnant frequency range, and that may mean that we can revert this procedure. In the next slide, we perform a reconstruction, and we see that unfortunately DMD did not capture the LCO behavior, neither for the spatial displacements or for the reconstruction displacement data. In the next slides, I show as well the spatial modes for 2.98 psi and the spatial modes for 3.15 psi on the next slide, and 3.15 psi. All of these slides show that the major motion of the wing was captured to be the first bending motion, as it is consistent with the experiment. In summary, an open source model using SU2 calculates and precise was analyzed and compared to the experiment into meshing approaches. We could observe that the refinement in the solid did not incur significant changes in the natural frequency modes. However, the refinement in the fluid played an important role. Additionally, we could observe a vortex breakdown phenomena for the refined model, which calls for further investigation. We also saw that DMD revealed a non-stagnant frequency range, and we are going to continue analyzing it to understand further. In the next time of my research for future work, I would like to focus on studying the phenomena that maintains the constant frequency, as well as doing different time step studies and understanding the impact that they have in the FSI analysis, and continue to analyze the displacement through DMD for the refined model. Thank you very much for your attention. Do you have any questions or comments?
Questions for Sheila?
We'll probably have to repeat it.
Can you comment on the specific methods, Sheila, you use to transfer stresses from the fluid to the solid side of the model?
Sorry, could you repeat the question, please?
Yeah, the question was about how you transfer stresses, shear stresses on the fluid applied on the walls of the solid. Can you comment on that?
So we did not focus on the shear stresses, but I believe that is done in precise. We mostly focused on the displacements and the forces only from SU2.
Okay, yeah, thank you, Sheila. One quick question from me, Sheila. You have two different mesh resolutions,
Yes.
and then at the LCO there was a very substantial difference between them, which means you may not be converged yet, and you are trying to match experiments. Have you tried resolving further, or do you have a limitation there on how resolved you can make your geometry?
Thank you very much. Actually, I believe that the time step may be the reason why it's not converging well. So recently we just started research with supercomputers and high performance computing, and I have started to run the simulation with lower time steps, and the results have started to differ a little bit. So I do believe, yes, that there is a limitation in computational power that may be leading to the results that we are having now.
Yeah. Do you explicit or implicit coupling?
Explicit coupling, I believe, yes. Explicit.
Explicit. Okay. Thank you very much, Sheila. I think that's it for today.
Thank you very much.
Okay, thank you, Sheila.